Hi everyone, we are back and we are going to start to talk about now Lecture 3, Defects in Crystalline Materials. And I always like to start off with this fabulous quote by Professor Sir Colin Humphreys. Crystals are like people, it's the defects in them which tend to make them interesting. And I think that's a very nice and true statement. So, we want to achieve, again, thermodynamic equilibrium, so we need to minimize essentially our free energy. And we have two knobs. And we've talked a bit about enthalpy and bonding. But now we're going to get into entropy, which is effectively maximizing the configurational states that our system can adopt. So if I have a perfect crystal, system 1, and I have a crystal here that has perhaps some point defects, and I know that my minus k natural log of omega, where omega is my number of microstates. So, how many ways can I reconfigure effectively my system here? So how many microstates can I create? So, if I have all of the atoms in a perfect crystal, there's only, one microstate. And that's going to lead my entropy saying 0, so the only way to lower my energy is to bond and to change essentially those interactions. So my entropy here is very, 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 very low. We want to increase entropy. Here, I could have an empty spot here. I can reconfigure it here. So there's lots of ways. There are many, many, many number of microstates, and I have much more entropic states that essentially, I have a much higher entropy exhibited by system 2. So my entropy of 2 is greater than my entropy of 1. So the cool part about this is that effectively, once we have any system that's non-zero temperature, and even at temperature of 0, the equilibrium state will most likely have imperfections. So you have an energy argument for why systems will actually, at equilibrium, contain a certain concentration of defects. And we're going to actually go ahead and calculate this for us in just a bit. But before we get into that, we want to look at crystalline defects. And so there's going to be 0, 1, 2, and 3-dimensional defects. And we're going to start with the 0D defects or point defects. So one of the most common types of point defects is a vacancy. So a vacancy effectively is where a site that's normally occupied is now unoccupied. So it can happen in quite a few ways. And actually we can kind of see some of our other defects here. So a vacancy, this is our lattice. Our lattice is this system of our blue, which is one type of atoms. And you see it has this regular order in this kind of this square. So there should be an atom here in this location, but it's empty. So that is a vacancy, and that is a 0D defect. Alternatively, I can have these sites in between where there are no atoms. And again, there should be no atoms here. So that's our equilibrium structure. Those sites are called interstitial sites. So I can have a defect where I have a self-interstitial. So you can imagine where the atom here inserts and moves and vibrates such that it occupies now this self-interstitial site. Or an interstitial site. And because it's of the same type, we call it self. This is distinct from a impurity interstitial site. So an atom of a different size or a different type, right? So here I have a small atom that fits in here, very similar to carbon when we look at kind of steel and how steel is formed. Alternatively, I could have a much bigger atom placed here as well. So that would also be an interstitial impurity. I could also have a substitutional impurity, whereby I replace, for example, one of these atoms, and I kill it off, with another atom of a different type. And that atom of a different type will obviously have a different size, and so that will cause effectively some strain in our system as well. So we kind of gave this hint about there will always be this equilibrium concentration of defects. Well, we can actually calculate this for vacancies. So we can go ahead and look at and assume I have some concentration of vacancies, little n. And I have n number of atoms. So my total number of sites is going to be equal to big N plus little n. So this is kind of conserved here. So the number of sites will always be conserved. So there's some combination of these. And to create a vacancy, I have to do work. So I'm going to have to put in work into my system. So I'm going to have to add that work. So that to form that vacancy. So we all know this expression. Excuse the minus sign over there. I'm always wondering about that minus sign. But anyways, we can look at our calculation for entropy here. And again, it's the number of microstates, the number of ways we can kind of distinguishable that we can arrange our system. So if I look at my configurational entropy here, and we can look at our two systems, we said that for the reference, the perfect crystal, that's just going to be 1. And we know distinguishable ways that we can look at our system. So we have to look at our total number of sites, n plus little n, permutation. This will be effectively very, very similar to our permutations, right? So the number of ways we can arrange these. So either a total number of sites, and then we're going to pick out effectively a set here. So you can kind of go back and look through those, look through that derivation, and you can kind of see what you get out of it. But anyways, we'll save that for, you can save that for another time for figuring out how that one works. But anyways, these are going to be the total number of ways that I can distinguishably arrange my system. So we can go ahead and move through the rest of this math. We can invoke essentially Stirling's approximation, which is right here. And we can write out the free energy of our system. And again, we're trying to find out when we minimize Gibbs. So we're going to take this function. And again, this is just the number of ways we can distinguishably, again, arrange our system. I can take my Gibbs free energy, and I want to minimize with respect to, because I want to know how many number of vacancies should exist at equilibrium. I'm going to set this equal to 0, and we can solve that. And eventually you get an expression that looks like, again, just solving it with respect to this, and we get this expression after some rearranging. Now, this x sub v is basically our concentration of vacancies. This is it's actually a site fraction, or it's basically it's number of vacancies over what? Our total number of sites. So this varies from 0 to 1, a dimensionless number. We know the energy to create essentially that defect here. This vibrational entropy component, it will, for most metals and most other systems, it's going to go to 1. So we can effectively ignore that. But the key thing here is we see that we have this relationship where the concentration of vacancies is related to what? The energy, obviously, to create that vacancy, but more importantly, a parameter that we can control, which is temperature. And this special relationship is this exponential relationship, and it's a Arrhenius dependence. It's an Arrhenius relationship. So we have to kind of focus in on this here. So this is a key component, effectively, to what we're working for. So, and we can look at essentially our Arrhenius plot here below. Now, oftentimes when you look at these Arrhenius relationships, which look like x of v equals some exponential minus delta hf divided by kt. It's often nicer, we want to plot it like this, the natural log of x of v of 1 over t. And the reason we do that is you'll actually see that, you'll see basically a straight line like this. Because if I take the natural log of this function, natural log of x of v, now I have, this exponential goes away, minus delta hf divided by k times 1 over t. And this looks like the same form, y equals m times x. If we're plotting, this is y and this is x. So now I can actually just measure my slope, and I know that my slope will be equal to minus delta hf divided by k. If I know my slope and I know my Boltzmann's constant, which we all know, I can solve for that enthalpy of fusion. Nice, right? Very nice way to plot something, again, to show people exactly, again, to show a graph that you can extract the most critical information just like that, just like that, just like that. So that's very, very good. Interstitials, we've talked about, it has a very similar relationship as well. The only thing that is different, or one of the key things that are different, is we will look at this delta H is effectively the enthalpy of formation to create a self-interstitial. And the energy of formation for basically a self-interstitial is going to be less for disympatric structures, but typically the delta H of formation for a self-interstitial is going to be larger than the delta H of formation for the creation of a vacancy. And why is that? Well, if I have a densely packed structure here, it's tough to squeeze in a molecule like this, and it's a little bit easier for those atoms to relax back, it's much easier for the atoms to relax back to those positions. And you can kind of see that or remember that from our Leonard-Jones potential, right? So if I have an atom that's at an equilibrium distance here, I'm going to pay less. If I move just this distance, right, here to here, I'm paying this much energy penalty. But if I move that same distance, let's kind of draw this out from here to here. If I move that same distance, this is an anharmonic solution. You can see if I draw out up here, I'm paying this energy penalty. So we don't want those atoms to be compact. It pays a higher energy penalty here. So those are self-interstitials and 0D defects. Excellent. Now, next time, we're going to start talking about alloys and, most importantly, Kroger-Vink notation. So we'll see you then. Thanks. Bye.